It is time to set our goals and introduce the framework we will use. Creating a machine learning algorithm ultimately means building a model that outputs correct information given that we've provided input data. For now, think of this model as a black box. We feed input and it delivers an output. For instance, we may want to create a model that predicts the weather tomorrow, given meteorological information for the past few days. The input we'll feed to the model could be metrics, such as temperature, humidity, and precipitation. The output we will obtain would be the weather forecast for tomorrow. Now, before we get comfortable and confident about the model's output, we must train the model. Training is a central concept in machine learning, as this is the process through which the model learns how to make sense of the input data. Once we have trained our model, we can simply feed it with data and obtain an output. Alright, the basic logic behind training an algorithm involves 4 ingredients: data, model, objective function, and an optimization algorithm. Let's explore each of them. First, we must prepare a certain amount of data to train with. Usually, this is historical data, which is readily available. Second, we need a model. The simplest model we can train is a linear model. In the weather forecast example, that would mean to find some coefficients, multiply each variable with them, and sum everything to get the output. As we will see later though, the linear model is just the tip of the iceberg. Stepping on the linear model, deep machine learning lets us create complicated non-linear models. They usually fit the data much better than a simple linear relationship. Awesome! The third ingredient is the objective function. So far, we took data, fed it to the model, and obtained an output. Of course, we want this output to be as close to reality as possible. That's where the objective function comes in. It estimates how correct the model's outputs are, on average. The entire machine learning framework boils down to optimizing this function. For example, if our function is measuring the prediction error of the model, we would want to minimize this error, or, in other words, minimize the objective function. Okay, our final ingredient is the optimization algorithm. It consists of the mechanics through which we vary the parameters of the model to optimize the objective function. For instance, if our weather forecast model is weather tomorrow equals W1 times temperature plus W2 times humidity, the optimization algorithm may go through values like 1.05 times temperature plus 1.2 times humidity, or 1.05 times temperature minus 1.2 times humidity, or 1.04 times temperature minus 1.19 times humidity, and so on. W1 and W2 are the parameters that will change. For each set of parameters, we would calculate the objective function. Then, we would choose the model with the highest predictive power. How do we know which one is the best? Well, it would be the one with an optimal objective function, wouldn't it? Alright, great. Later, we'll reiterate what we've said here because there will be separate lessons for the ingredients of an algorithm. Did you notice we said 4 ingredients instead of saying 4 steps? This is intentional, as the machine learning process is iterative. We feed data into the model and compare the accuracy through the objective function. Then, we vary the model's parameters and repeat the operation. When we reach a point after which we can no longer optimize, or we don't need to, we would stop, since we would have found a good enough solution to our problem. In this section, we look at each of the basic building blocks in more detail. At the end, we will conclude by creating our first machine learning algorithm. Sounds exciting? Well, it definitely is. Thanks for watching. In this lesson, we will explore the concept of training the model through the data. Let's start with an example. You have a coffee machine that doesn't know how to make coffee. In a non-machine learning setting, we would need to incorporate the instructions in the machine's electronics, or at least that's how all coffee machines I have seen work. For instance, the engineers may set the machine's electronics to: first, grind 20 grams of coffee beans. Second, heat the water to 200 degrees Fahrenheit. Third, pour 100 milliliters through the ground coffee into the cup. Now, in a machine learning setting, we won't explicitly provide instructions to the machine. Instead, we just need to state our goals. In the coffee machine case, that would be produce a cup of coffee. Then we would let the machine work out the problem on its own. The machine learning process is a kind of trial and error training. The machine would try various combinations of grinding, heating, and pouring. Most would not make sense. The machine would try heating the water and pouring it before grinding the coffee, resulting in a cup of hot water. Or it may grind the coffee and pour the water without heating the water. Anyhow, after thousands of trials and errors, the algorithm would train itself to reach the set goal every time. It can make a cup of coffee. It is possible that it will learn to make the best coffee you have ever tried, much better than the one obtained by following a set of instructions. That's because it would have gone through so many more recipes than a human would ever be able to. A reasonable optimization algorithm would not try all combinations, as there are usually inexhaustibly many other options. In the coffee example, if the coffee machine learns that grinding the coffee has to go before pouring the water, it would not waste time attempting it in the wrong order. We'll talk more about optimization algorithms soon, don't worry. This example shows us why machine learning is so powerful. It allows systems to learn on their own situations, where humans cannot define a rigid set of rules for the computer to follow. Even if we can define a set of rules, an algorithm can probably provide a better one. Before wrapping up, let's explore another interesting instance: self-driving cars. Contrary to what many people think, self-driving cars don't follow rules such as avoid curbs. Essentially, they train on thousands of hours of footage of real people driving and learn how to mimic them efficiently. It is not the set of rules they know, but the final goal. The final goal fundamentally is to drive safe and efficiently. Avoid curbs, don't bump into other cars, don't go over the speed limit, stop at red lights, and so on. Okay, now that we know training data is at the core of the process, we can differentiate between different types of machine learning. Stay tuned, and thanks for watching. There are three major types of machine learning: supervised, unsupervised, and reinforcement. Supervised learning refers to the case where we provide the algorithm with inputs and their corresponding desired outputs. Based on this information, it learns how to produce outputs as close to the ones we are looking for. Both examples, the one about the weather forecast and the one about preparing coffee, illustrated supervised learning. That was intentional, as it is the focus of this course. Alright. The second type of machine learning is unsupervised learning. In unsupervised learning, we feed inputs, but there are no target outputs. This means we don't tell the algorithm exactly what our goal is. Instead, we ask it to find some sort of dependence or underlying logic in the data provided. For instance, imagine we administrate the website catsanddoggos.com. Users have the option to submit photos of their cats or dogs to the website. Once a photo has been submitted, we would like it to be automatically classified in the subpage cats or the subpage dogs. In supervised learning, we would train the algorithm on a dataset of, say, 1,000 cat photos and 1,000 dog photos. Each would be labeled cat or dog. The model would then learn how to interpret an input picture as either a cat or a dog, minimizing mismatches over the training set. Sometimes, however, we may not have the resources or the need to label the whole dataset. In the previous dataset, there was a person who manually labeled all 2,000 pictures. Now, imagine a dataset of 2 million pictures. If it takes a person 5 seconds to label a picture, a dataset of 2 million observations would take around 2,800 hours or 345 working days to label all pictures. With unsupervised learning, though, we can train the algorithm without labeling the photos or in an unsupervised way. We could simply ask it to split them into 2 groups based on visual similarities. The result would be 2 groups that are unlabeled. Once we have obtained that, we can examine them and say, "Oh yes, the first set is dogs and the second set is cats. Thanks, algorithm." Unsupervised learning is especially useful when our goal is to split a dataset into a certain number of categories, which we do not know prior to implementing it. That, by the way, is called clustering. Okay, the final type of machine learning is reinforcement learning. Without digging too deep into it, with reinforcement learning, we would train a model to act in an environment based on the rewards it receives. It is much like training your pet and rewarding it with treats every time it achieves a goal, sits, rolls over, or gives you a pawn. In the same way, the machine learning algorithm could be taught how to play Super Mario by rewarding it for progressing with an increase in score. Alright. Supervised learning is the focus of this course. That is because it is the simplest and most commonly used. To exhaust the topic, supervised learning could be divided into additional subtypes: classification and regression. The difference is very straightforward. Classification supervised learning models provide outputs, which are categories, such as cats or dogs. In regression supervised learning models, the outputs will be of numerical type. For instance, predicting the euro-dollar exchange rate will always give us a continuous number, like 1.21 or 1.19. In this course, we will create both classification and regression algorithms. Stick around, and thanks for watching. So far, we learned what training a dataset involves and established that we will focus on supervised learning. It is time for the second piece of the puzzle, the model. Let's consider a variable x. The function f of x gives us an output y. Y is a function of x, but we don't know this function. We want to make the algorithm find out on its own. This is done by providing it with many pairs of observations of x and y as possible and following the methodologies to come. Alright, let's start with the simplest model possible, the linear model. Despite appearing oversimplified, it is extremely important as it is the basis for more complicated models, including non-linear ones. In the linear model universe, f of x is x times w plus b. X is the input we have. In the traditional statistical jargon, we would call w the coefficient of x, and b would be the intercept. In machine learning though, w is called the weight or weights when we have more than one parameter. B is called the bias or biases. There are many ways to define the linear model. W times x, x times w, x transpose times w, or w transpose times x. It doesn't matter. We will keep the linear model simple and represent it in the following way: x times w plus b. The goal of the machine learning algorithm would be to find such values for w and b so the output of x times w plus b is as close to the observed values as possible. Okay, let's see an example. Say our goal is to predict the price of an apartment. We may do that based on its size. So, the input x is the size. X times w plus b is the model we are using. The calculation of this expression gives us the price, or the output y. Let's input real values. The size of an apartment is 743 square feet. A possible model for predicting its price is x times 336.1 minus 3237.51. The weight is 336.1 and the bias is minus 3237.51. If we calculate the output following this model for a 743 square feet apartment, we would obtain a price of $246,484.79. Similarly, given an apartment of a different size, say 1,000 square feet, our model would predict a price of $332,862.49. Knowing the size of any apartment, we can get a prediction of its price based on the linear model. Note, this example oversimplifies how things work in practice. But don't worry, we will get there soon enough. Thanks for watching. Let's extend our little real estate valuation model to multiple inputs. What if we had additional information? Say, the apartments we are valuing are located by the sea. The closer an apartment is to the beach, the higher the price should be, right? Well, a better linear model would predict the price, based on both size and proximity to the beach. The linear model tackling this issue is the price of an apartment equals its size, times the weight of size, plus the apartment's proximity to the beach, times the weight of proximity plus the bias. If we want to state this expression in linear algebraic terms, we can use the same framework as before, x times w plus b. X and w are both vectors. X is 1 by 2 and w is 2 by 1. Multiplying x and w would give us a scalar, as 1 by 2 times 2 by 1 is equal to a 1 by 1 shape. Let's continue our housing example with the two input variables. The output y is equal to x times w plus b. X has two elements, a size of 743 and a distance from the beach of 1.21 miles. W has two elements too, one for each input. The values are 403.77 and minus 15,212. This time the bias is plus 1,212.45. To calculate the new projected price, we must multiply 743 times 403.77, then subtract 1.21 times 15,512, and add the bias, 1,012.45. The result is $282,444.04. Similarly, if the 1,000 square feet apartment is 2 miles away from the beach, its price becomes $373,958.45. Notice that the weight of the distance from the beach is negative. This is because we expect this variable to have a negative impact on an apartment's price. The greater the distance from the beach, the lower the price. Alright, in the next lesson, we will extend the model to its most general form, multiple inputs and multiple outputs. Stay tuned. Okay, let's apply the linear model logic for multiple output variables. Here's our new situation. We may be interested in predicting not only the price of the apartment when buying it, but also the price for which we can rent it out. Our inputs are unchanged, size and proximity to the beach. This time though, we have two outputs. Therefore, we can create two linear models. The price as a function of the size and proximity to the beach, and the rent as a function of the size and proximity to the beach. y1 equals x1 times w11 plus x2 times w21 plus b1, and y2 equals x2 times w12 plus x2 times w22 plus b2. Notice the indices of the weights. The first number refers to the respective input, while the second to the output. We have two outputs, two inputs, four weights, and two biases. The number of weights depends on the inputs and the outputs. There is a different weight for each input in each equation. In general, if we have k inputs and m outputs, the number of weights would be k times m. The number of biases is equal to the number of outputs, m. Let's see this in linear algebraic terms. Y equals x times w plus b. Two outputs, two inputs, four weights, and two biases. Let the weights for the apartment price be equal to 403.77 and minus 15,512 as before. And the weights for the rent be equal to 13.9 and minus 484.75. So, these are our W11, W12, W21, and W22. The biases are 1,112.45 and 212.34. The inputs are the same as before, 743 and 1.21 miles. So, the first output, y1, is found in the familiar way. 743 times 403.77, then subtract 1.21 times 15,512, and add the bias, 1,212.45. The result is $282,444.04, and that's the price of the apartment. The second output, y2, is found by 743 times 13.9 minus 484.75 times 1.21 plus 212.34. The result is $9,952.79. So, basically you can buy the house for around $282K and rent it out for $10K. That's how we use the same model, x times w plus b, to represent two linear relationships. Notice how the previous example is actually part of this one. Here are the respective output, inputs, weights, and bias. Finally, I would like to point out that this was only one observation. We could extend this example to many inputs, outputs, and observations. The output matrix will be n by m. where n is the number of observations and m is the number of output variables. The input matrix will be n by k, where k is the number of input variables. The weights' matrix remains the same, as the weights don't change depending on the number of observations. The same applies to the biases. This last bit is extremely important. It shows us we can feed as much data in our model as we want to, and it won't change, as each model is determined solely by the weights and the biases. This property will greatly help us when creating machine learning algorithms. We vary only the values of the weights and the biases, but the logic of the model stays the same. Cool. In the next lesson, we will see why the linear model is useful for solving problems. Thanks for watching. Picture time. Let's stop for a second and illustrate two situations in which machine learning and neural networks come in handy. You are probably wondering how a linear model can solve our cats and dogs photo problem. Well, it depends on the data. Here is a scatterplot of a dataset consisting of animal photos. Let the blue dots be the dogs' photos from one of our previous examples, and the orange ones, the cats. A linear model, or a straight line, can solve this problem fairly easily. Everything below the line is one category, while everything above it is the other. In this situation, we have a classification problem. We are trying to classify the photos into dogs and cats. Such a model is called a linear classifier. It looks useful, right? Well, that's true, because the data represented in the graph is linearly separable. But what about this case? We have only several categories, but we can't fit a straight line through them. This data is not linearly separable. Therefore, we must use a nonlinear model. Well, we will learn how to handle such problems in the section where we will learn about deep neural networks. Finally, to be true to our promises, we will show you a regression picture. Here is the graph of our apartment price example. Each point represents an apartment. A linear model explains the data well, right? This is one of the well-known linear relationships. However, different regression problems may not necessarily be solved by a linear model. Look at this graph for instance. Totally not linear. Once again, that's a topic for deep neural networks. For now, you have learned the most fundamental modeling block, the linear model. Thanks for watching. It is time for the third building block of the machine learning algorithm, the objective function. The objective function is the measure used to evaluate how well the model's outputs match the desired correct values. In this lesson, we will elaborate on that. Objective functions are generally split into two types, loss functions and reward functions. Loss functions are also called cost functions. The lower the loss function, the higher the level of accuracy of the model. Most often, we work with loss functions. An intuitive example is a loss function that measures the error of prediction. We want to minimize the error of prediction, thus minimize the loss. Reward functions, on the other hand, are basically the opposite of loss functions. The higher the reward function, the higher the level of accuracy of the model. Usually, reward functions are used in reinforcement learning, where the goal is to maximize a specific result. Remember the algorithm we mentioned earlier? The one playing Super Mario? The score obtained by the algorithm while playing the game is the reward function. Maximizing the final score would mean maximizing the reward function. Alright, when dealing with supervised learning, we normally encounter loss functions. Therefore, in this course, we'll deal mostly with them. In our next video, we will explore the two most common loss functions. Thanks for watching. Earlier, we divided supervised learning into two types, regression and classification. We will take the same approach here and consider two of the most common types of loss functions. Each is used with one of the two types of supervised learning. Note that the objective function is a separate block in our framework from the model. That is to say that what we are going to discuss now is generally true for all models, regardless of their linearity. Okay. First, we should define another concept, called the target, denoted by T. The target is essentially the desired value at which we are aiming. Generally, we want our output, y, to be as close as possible to the target, t. In the cats and dogs example we've been employing so far, the targets, would be the labels we assign to each photo. So, we are 100% sure these values are correct. They are the values we aspire to. The y values are the outputs of our model. The machine learning algorithm aims to find a function of x that outputs values as close to the targets as possible. Using this new notation, the loss function evaluates the accuracy of the outputs regarding the targets. Alright, let's see the two common functions we talked about. First, we will talk about regressions. I'd like to remind you that the outputs of a regression are continuous numbers. A commonly used loss function is the squared loss, also called L2 norm loss in the machine learning realm. The method for calculating it equals the least squares method used in statistics. Mathematically, it looks like this. The sum of the squared differences between the output values, y, and the targets, t. Naturally, the lower this sum is, the lower the error of prediction. Therefore, the lower the cost function. Okay, we will check out a common loss function for classification in our next lesson. Thanks for watching. Hi, and welcome back. What about classification? We discussed that the output of a regression is a number, but for classification, things are different. Since the outputs are categories, like cats and dogs, we need a better suited strategy. The most common loss function used for classification is cross-entropy, and it is defined as L of y and t equals minus the sum of the targets times the natural log of the outputs. Time for an example before I lose your interest. Let's consider our cats and dogs problem. This time, we will have a third category, horse. Here's an image labeled as dog. The label is the target. But how does it look in numerical terms? Well, the target vector t for this photo would be 0, 1, 0. The first 0 means it is not a cat, the 1 shows it is a dog, and the third 0 indicates it is not a horse. Okay, let's examine a different image. This time, it will be labeled horse. Its target vector is 0, 0, 1. Imagine the outputs of our model for these two images are 0.4, 0.4, 0.2 for the first image, and 0.1, 0.2, 0.7 for the second. After some machine learning transformations, these vectors show the probabilities for each photo to be a cat, a dog, or a horse. We will learn how to create these vectors later in the course. For now, we just need to know how to interpret them. The first vector shows that, according to our algorithm, there is a 0.4 or a 40% chance that the first photo is a cat, 40% it is a dog, and 20% it is a horse. So that's the interpretation of these vectors. What about the cross-entropy of each photo? The cross-entropy loss for the first image is minus 0 times natural log of 0.4, minus 1 times natural log of 0.4, minus 0 times natural log of 0.2. This equals approximately 0.92. The cross-entropy loss for the second image is minus 0 times natural log of 0.1, minus 0 times the natural log of 0.2, minus 1 times the natural log of 0.7, which equals approximately 0.36. As we already know, the lower the loss function, or the cross-entropy in this case, the more accurate the model. So, what's the meaning of these two cross-entropies? They show the second loss is lower, therefore, its prediction is superior. This is what we expected. For the first image, the model was not sure if the photo was of a dog or a cat. There was an equal 40% probability for both options. We can oppose this to the second photo, where the model was 70% sure it was a horse. Thus, the cross-entropy was lower. Okay. An important note is that, with classification, our target vectors consist of a bunch of zeros and a 1, which indicates the correct category. Therefore, we could simplify the above formulas too. Minus the log of the probability of the output for the correct answer. Here's an illustration of how our initial formulas would change. Alright, those were examples of commonly used loss functions for regression and classification. Most regression and classification problems are solved by using them. But there are other loss functions that can help us resolve a problem. We must emphasize that any function that holds the basic property of being higher for worse results and lower for better results can be a loss function. We will often use this observation when coding. It will all become clear when we see them in action. That's all for now. Thanks for watching. We have reached the last piece of the puzzle before we can start building our first machine learning algorithm. So far, we have learned, at least conceptually, how to input data into a model and measure how close to the targets are the outputs we obtain through the objective function. However, the actual optimization process happens when the optimization algorithm varies the model's parameters until the loss function has been minimized. In the context of the linear model, this implies varying W and B. Okay? The simplest and the most fundamental optimization algorithm is the gradient descent. I would like to remind you that the gradient is the multivariate generalization of the derivative concept. Let's first consider a non-machine learning example to understand the logic behind the gradient descent. Here's a function f of x equal to 5 times x squared plus 3 times x minus 4. Our goal is to find the minimum of this function using the gradient descent methodology. The first step is to find the first derivative of the function. In our case, it is 10 times x plus 3. The second step would be to choose any arbitrary number, for example, x0 equals 4. x0 is the proper way to say x0. Then we calculate a different number, x1, following the update rule. xi plus 1 equals xi minus eta times the first derivative of the function at xi. x1 is equal to 4 minus eta times 10 times 4 plus 3, or 4 minus eta times 43. So what is eta? This is the learning rate. It is the rate at which the machine learning algorithm forgets old beliefs for new ones. We choose the learning rate for each case. By the end of this lecture, the concept of eta will be clearer. Using the update rule, we can find x2, x3, and so on. After conducting the update operation long enough, the values will eventually stop updating. That is the point at which we know we have reached the minimum of the function. This is because the first derivative of the function is 0 when we have reached the minimum. So, the update rule. xi plus 1 equals xi minus eta times the first derivative at xi will become xi plus 1 equals xi minus 0, or xi plus 1 equals xi. Therefore, the update rule will no longer update. Let's illustrate this with an example. Let's take an eta of 0.01. We start descending. x1 is equal to 3.57. x2 is equal to 3.18, and so on. Around the 85th observation, we see our sequence doesn't change anymore. It has converged to minus 0.3. Once the minimum is reached, all subsequent values are equal to it, since our update rule has become xi plus 1 equals xi minus 0. Graphically, the gradient descent looks like this. We start from any arbitrary point and descend to the minimum. Alright, the speed of minimization depends on the eta. Let's try with an eta of 0.1. We have converged to the minimum of minus 0.3 after the first iteration. Now, knowing the minimum is minus 0.3, let's see an eta of 0.001. This step is so small that we need approximately 900 iterations before we reach the desired value. We descend to the same extremum but in a much slower manner. Finally, I'll try with an eta of 0.2. We obtain a sequence of 4 and minus 4.6 until infinity. No matter how many iterations we execute, our sequence will never reach minus 0.3. We already know minus 0.3 is the desired value, but if we didn't, we would be deceived. This situation is called oscillation. We bounce around the minimum value, but we never reach it. We can use 4 or minus 4.6 in the algorithm, but this won't be its true minimum. Graphically, we are stuck into these 2 points, never reaching the minimum. Now that we have seen different learning rates and their performance, let's state this rule. Generally, we want the learning rate to be high enough so we can reach the closest minimum after repeating the operation in a rational amount of time. So, perhaps 0.001 was too small for this function. At the same time, we want eta to be low enough so we are sure we reach the minimum and don't oscillate around it, like in the case where we chose an eta of 0.2. In the sections in which we will study deep learning, we will discuss a few smarter techniques that would allow us to choose the right rate. Alright, there are several key takeaways from this lesson. First, using gradient descent, we can find the minimum value of a function through a trial and error method. That's just how computers think. Second, there is an update rule that allows us to cherry pick the trials so we can reach the minimum faster. Each consequent trial is better than the previous one with a nice update rule. Third, we must think about the learning rate, which has to be high enough so we don't iterate forever and low enough so we don't oscillate forever. Finally, once we have converged, we should stop updating, or as we will see in the coding example, we should break the loop. One way to know we have converged is when the difference between the term at place I plus 1 and place I is 0.001. Once again, that's a topic we'll see in more detail later. Please download and look at the Excel file associated with the gradient descent, available in the course resources section. We encourage you to play around with the learning rate or the arbitrarily chosen number x0 and see what happens. This will give you a good intuition about the learning rate, which is central to teaching the algorithm. In the next lesson, we will generalize this concept to the n-parameter gradient descent. Thanks for watching. If we want to create working models that can be easily adapted to different problems, you must understand the drivers of a machine learning algorithm. That is why we've covered several theoretical steps. And this is where the introductory part ends. We will step on the one-dimensional gradient descent concept and explain the concept of the gradient descent used in machine learning. In addition, we'll apply what we've learned about linear models and loss functions. It will all fall in place. Promise. Let's consider the linear model we have discussed so far. The inputs, x, times the weights, w, plus the biases, b, are equal to the outputs, y. Now, each output yi can be represented using the linear model equation, where the input is just the corresponding xi. The weights and the bias remain unchanged. Using our apartment size price example, yi would be the price of a single apartment. The corresponding xi would be information we have about this apartment. In essence, we are taking a single observation. Therefore, the output yi is a scalar and is equal to the corresponding xi times w plus the bias. Naturally, we are interested in the ith target, so ti. This will be the target to which we will compare the output yi. Alright, time to pick the loss function we'll use. Usually, we denote the loss function with L, and in brackets we put the outputs and the targets, as the loss function depends on these arguments. L is for loss, but we can have C for cost, E for error, and so on. Depending on the framework you are using, notations could differ, but they carry the same meaning. Okay, since we've only discussed two types of loss functions, the L2 norm loss and the cross entropy, obviously, our choice is limited to them. We will look into a regression example, so let's take the L2 norm loss and augment it a bit by dividing it by 2. This is conventional, and we will see why in just a minute. A division by the constant of 2 does not change the nature of the loss function, as it is still lower for better predictions. The machine learning algorithm will not be affected. We emphasized this in the objective function lecture. Every function holding the general property to be lower for higher accuracy is a loss function. Division by some constant changes nothing. Make sure you remember what the gradient is, and let's start working in the multidimensional space. To perform the gradient descent, we need old beliefs, which will be updated on each step. Remember? Well, the update rule. xi plus 1 equals xi minus eta times the first derivative at xi becomes wi plus 1 equals wi minus eta times the gradient of the loss function with respect to wi for the weights, and bi plus 1 equals bi minus eta times the gradient of the loss function with respect to bi for the biases. It is basically the same, but for a matrix W and a vector B instead of a number x. Okay. We want to minimize the loss function by varying the weights and the biases. This means we are trying to optimize the loss function regarding W and B. Mathematically, it looks like this. The gradient with respect to W of the loss function is equal to the sum of the gradient of 1/2 times yi minus ti squared with respect to W. From the linear model, yi is equal to xi times W plus the bias where W and x are matrices, and this is why we've applied bold formatting. So, let's plug that in the formula. Running the operations, we obtain the sum of xi times yi minus ti. Please take a more detailed look in the course notes. It is useful to combine yi minus ti into a new variable called delta. Delta is often used to measure differences. This notion will come in handy when we start coding in Python and when we start dealing with deeper neural networks. The final output becomes the sum of xi times delta I with respect to I. So, we calculate that expression for each observation and then sum them all. Okay, analogically, the gradient of the loss function with respect to the bias is the sum of delta I. Notice that the 1/2 we introduced canceled out the 2 we obtained when differentiating the square. That's why we included it, to get a neater result. Finally, let's go back to our update rule. We said the generalized rule is wi plus 1 equals wi minus eta times the gradient of the loss function with respect to wi. Replacing the gradient with what we found here, we obtain wi plus 1 equals wi minus eta times the sum of xi times delta I. Analogically, the update rule for the biases is bi plus 1 equals bi minus eta times the sum of delta I. Alright, this was the generalized gradient descent of a linear model. We can use it to minimize the cost function and train our model to enable it to produce valuable insights from our data. This is all we promised you at the beginning of this section, and we've delivered. Maybe a bit more, but nothing less. Okay, great. We are in good shape to create our first machine learning algorithm in Python. See you in our next lesson.